If this is the original graph, what is an inflection point? Where the concavity changes. So for part A, if this is the original, I'm just looking for where the concavity changes. So this graph is curved down, and then all of a sudden it's curved up. So right here would be an inflection point. So when x is 3. And then the next place would be at 5. And that's just because the concavity changes. That's what an inflection point is. It's asking you where your concavity changes. Are you guys okay with that? Mm-hmm. So then, B, I'm going to say, okay, let's suppose this is the first derivative that I've drawn the graph of. So we have to think. An inflection point is where the concavity derives, or where the concavity changes. It's where the second derivative is 0. So if I'm looking at the first derivative, the second derivative would be 0 anywhere this has a horizontal tangent line. Where do we have horizontal tangent lines? 2, 4, and 6. Do you guys understand that? Okay. C. If this is the second derivative, the second derivative, inflection points are where the second derivative is 0. So if I'm looking at the second derivative, I just need to know where is it 0. So that's at 1, 4, and 7. And that's because it equals 0 there. We know inflection point is where the concavity changes. It's where the second derivative is 0. So if I'm looking at the graph of the second derivative, I just need to know where it's 0. Does that make sense to everybody? All right. Let me ask you another question. Since we struggled with this a little bit, can I make up another question about this graph?
What's the explanation for B?
Because you would have a horizontal tangent line there. Basically, your maximums or minimums are where your next derivative would equal 0. What if I said, this is the graph of f prime? So I'm looking at the derivative. Can you tell me where function f would have a max or a min? So if I'm looking at the first derivative, okay, think about a graph. If I ask you to find the maxes and mins, what do? You do the first derivative and find out where it is 0. So we would have one everywhere this was 0, which is at 1, 4, and 7. Can you tell me which of those would be maxes and which ones would be mins? So we know these 3 points. If your first derivative is negative, what does that tell you about the original graph? It was decreasing, and then the derivative was positive, so the graph was increasing. So what happens at 1? A max or a min? A min at 1. Okay, what about at 4? It was positive, so increasing, and then still positive, so still increasing. So does anything happen there? Okay. At 7, it was positive, so increasing, then negative, so decreasing. So increasing to decreasing would be a max at 7. Does that make sense? All right, so question 15 is kind of related to that. I'm assuming you guys would like to work out 15 as well. So it tells us we are looking at the graph of the derivative, so kind of like the question I just asked you. And I want to know, when is this graph increasing or decreasing? So if we're looking at the derivative, how do you know if the original was increasing? What should be true about the derivative? It should be positive. So this graph is positive from where to where? 0 to 1 and 3 to 5. So it's decreasing where it's negative, which is 1 to 3 and 5 to 6. The next question asked, where do we have a maximum or a minimum? So that would be where it was 0. All right, so at 1, it went from increasing to decreasing, so 1 would be a max. At 3, it went from decreasing to increasing, so that would be a min. At 5, it went from increasing to decreasing, so that is also a max. So we would have a max at 1 and 5 and a min at 3. Does that make sense to everybody? Any other questions about that? Did I have any more questions on the study guide with the graphs like this? Let's go ahead and, can we talk about number 11 real quick while I have this turned on? All right. Absolute and local maxes and mins. Remember, absolute is the highest or lowest on the entire graph. They can be endpoints. Local cannot be endpoints. So absolute max, the actual highest my graph ever gets, is right here. So that is the point 4, 5. So 4, 5 is your max. The lowest my graph ever gets is an open circle. So does that count? No, so there's no absolute min. All right, so then we go through and look for local maxes and mins. Those can't be the endpoints. Right here, this would be a local max, but it's an open circle, so it doesn't count. But this point right below it, what would that be? That would be a local min at 1, 3, because it's lower than the points around it. Right here at 2, 2, that would be a local min. My absolute max is also a local max at 4, 5. At 5, 3, we would have a local min. And at 6, 4, this would be a local max. Is that okay with everybody? Let's see. Trying to make sure we hit all of the big things. So question 12 is also about absolute maxes and mins. Do you guys remember how we found those? What did we have to do?
Find the critical points.
So let's go ahead and we'll work out number 12. So my function was 4x plus 8 to the 1/3. So in order to get your critical points, what do you have to do? Derivative. So the 1/3 comes down, inside stays the same, subtract 1 from the power, times the derivative of the inside. If you want to rewrite this, a -2/3 means you have the cube root of that squared on the bottom. So critical points are anywhere this is 0 or undefined. If you have a fraction, you're really just looking at where is the top 0 and where's the bottom 0. Does the top ever equal 0? What would make the bottom 0? -2. Does everybody see that? Okay, so just in general, when we go through graphing, we find maxes and mins, but we don't usually do absolute maxes and mins. If I ask you for the absolute, what do I need to do now?
The endpoints and the critical points?
Right, you have to take the original endpoints and your critical points and plug those back into the graph to get your highest and lowest. What if I had also got a critical point of, let's say, 2? You wouldn't use it because it's not in your interval, so you might get extras. All right, so if I plug -5 into my original, we get, let's just do it on the calculator. So the cube root of, so we get -2.289. If you plug in a -2, you get 0. If you plug in a 0, you get 2. So where is my absolute max?
0.
And my absolute min? Are we okay with this? So if I ask you to do absolute max and min, we can handle that. So then we talked about mean value theorem and Rolle's theorem. I kind of have a couple sets of questions on those. 13 and 14 involve them, but I think, just in case I don't have time to work out everything, I'd rather work through 8 and 9 because, well, actually 6 and 7 are the conditions, 8 and 9 I think give us the whole picture. So you have to know what these two theorems tell you and what your criteria are for those. So that might be some good multiple choice questions on your test. I always put some of those, you know, those criteria. That would be a good question there. So question number 8 says, verify my function satisfies the hypotheses of Rolle's theorem on the interval 1 to 3. And then find all the numbers that satisfy the conclusion. All right, remember mean value theorem and Rolle's theorem start off the same. They have the same first two conditions. Rolle's theorem is the more specific. It has a third condition. What are the first two conditions? Yeah, it has to be continuous and differentiable, right? But we can just say, since it's a polynomial, so it is continuous and differentiable. That's the first one.
And how do you do it when it's not?
You basically look at where it's undefined. So if it's like,
Oh, if it's in the interval.
this wouldn't be continuous and differentiable at 0, so you would check if that's in your interval or not.
Okay.
Rolle's theorem has a third criteria. It says that the endpoints have to be equal. So Rolle's theorem, my endpoints are equal. So if you plug a 1 into the original, we get -4. If we plug in 3, we get 5 minus 36 plus 27. So we also get -4. So these endpoints are equal. So that means we can use Rolle's theorem. Then what does Rolle's theorem tell you?
There's a number C.
Where what is true?
In 1 and 3.
There's a number between 1 and 3
That equals 0.
where the derivative equals 0. So we do the derivative. And that has to equal 0. And we get 2. So is 2 in my interval? Yep. So we're done. So, mean value theorem and Rolle's theorem. We have to be continuous and differentiable. Rolle's theorem says then the endpoints are equal, so the derivative is 0. Mean value theorem is a little more broad. It says if it's a polynomial or if it's continuous and differentiable, then somewhere the derivative equals the slope between the endpoints. Now that's really kind of the same thing. If these endpoints are equal, if you did their slope, you would get 0. So Rolle's theorem is really just a special case of the mean value theorem. So question number 9. We look at this one. Our interval is -2 to +2. And we want somewhere where the derivative equals the slope between the endpoints. So mean value theorem only has 2 criteria. It's the same as the first 2 of Rolle's. So this is a polynomial, so it is continuous and differentiable. Then we have to get the slope between the endpoints. So if you plug in a -2, you get -8 plus 6 plus 2, which is 0. You plug in a 2, you get 8 minus 6 plus 2 is 4. So we have these 2 points. Is everybody with me there? So then we have to find the slope between them. So we know slope is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So we get 1. So mean value theorem says the derivative will equal 1. So if we do the derivative, set that equal to 1. Get rid of a square, you square root, plus and minus. 2 over radical 3, or if you multiply the radical on top and bottom, that's 2 radical 3 over 3. My interval was -2 to 2. Are both of those in my interval? They are. So we have 2 numbers this time. So I'm going to ask you mean value theorem and Rolle's theorem, probably 1 question on each, probably those multiple choice questions. So just make sure they're not hard, you just have to remember what the theorems tell you. So you might need to look back over that. Are we okay with that one? Alright. Trying to make sure we get all of the key things that I was worried about you forgetting. You guys remember how to find all your critical numbers, right? Alright, let's look at question number 2, finding the asymptotes. So your vertical asymptotes, how do we get those?
The bottom is 0.
So we would have to start off by factoring the denominator, so that would break into x plus 2, x minus 1. So the vertical asymptotes, they are lines, so I expect equations. So that would be x equals -2 and x equals 1. What do you have to do for the horizontal? As x approaches positive and negative infinity. I'm just going to go off the original. If you just plug in infinity right now, you get infinity divided by infinity. Is that helpful? No. So what is our trick?
Or with the first part of x.
So what did you guys multiply by?
That's great.
So we would get 2 over x plus 1 1 over x squared over 1 plus 1 over x minus 2 over x squared. We know that if you have a number over infinity, it turns into 0. So we have 0 plus 0 over 1 plus 0 minus 0. So we get 0 over 1, which is 0. So the horizontal asymptote would be y equals 0. Passed. It tells us that the second derivative is continuous. So that just means there's no asymptotes. So part A says f prime of 2 equals 0. If the first derivative is 0, what's happening here?
There's a horizontal maximum.
That's a critical point, so it's a maximum or a minimum. And it tells us my second derivative is equal to a negative 5. Second derivative gives us concavity. If it's negative, what does that tell us about our graph? So this graph is curved downward. So was it a maximum or a minimum? It's a maximum. So all we know there is you have a maximum at x equals 2. B. If the first derivative is 0, so if the derivative is 0, what's that mean?
Maximum.
And the second derivative is 0. What does that mean? What happens when the second derivative is 0? It's an inflection point. So my concavity is changing. So if it's an inflection point, the concavity is changing there. I don't know how it's changing. I don't know if it's changing from concave up to concave down or vice versa. Then do we know if it's a maximum or a minimum at 2? No. So there's really no conclusion here. We don't know anything. Except that 6 is both a critical point and an inflection point. That's really all it tells us. I'm going to give you another one. These are tricky. So let's say I told you that the second derivative is 0. Alright. So second derivative equals 0. What does that mean is happening at 1? It's an inflection point. The second derivative is less than 0 if x was less than 1. So what does that mean if the second derivative is less than 0? It's concave down. And then it was, the second derivative is greater than 0 after 1. So that means it was concave up. So we were concave down, so it was curved downwards. And then it switched to concave up. So what's really the only thing you can tell me about this graph? It kind of looks like this. What happens at 1? Yeah, all that's really telling us is there's an inflection point here. This type of question will probably be a multiple choice type question. So that gives you a little more idea of where I'm going with it. You know, am I wanting you to notice an inflection point or a maximum or minimum, those kinds of things. So it would be more of a weeding out process. You know, look at the answer choices and say, okay, it told me this. Does that mean there's a maximum at 1? No, all I know is the concavity change, so it's not that. So that would be a multiple choice type question on your test. Is that one okay? Do we need to do number 4, another absolute maximum question? You guys remember how to do those? We did one of them already. So you do find your critical points and test your critical points and endpoints, so we can handle that. All right, do you want me to work through one of A, B, or C on question 1? So your test is going to have 2 complete graphing problems like this. So one of them will be a polynomial, and one of them will be a rational function. All right, so do you want me to work out one of those? Do you have a preference?
C.
C? All right, so on these types of questions on your test, I will first say, give me the domain. So when I look at this, what do you have to do to find your domain? Figure out what makes the bottom 0. We know that in a fraction, the bottom can't be 0. So x can't be positive or negative 2. In general, I expect interval notation, but if it's more than one value, you can just list it. But if I just gotten that x couldn't be 2, then I want you to write negative infinity to 2, union 2 to infinity for your domain. All right? Second question is intercepts. So I will ask you to find those. How do you find the X-intercept? It's when your y equals 0. So if you multiply off the bottom, you just get x equals 0. How do you find a Y-intercept? Plug in 0 for all of your x's and you get 0. So on my graph, I can already say I have a point at 0, 0. C, I asked symmetry on the study guide, but I told you that I'm not going to ask that, and I told you to skip that part because I did not cover that. D, so I will ask you for the asymptotes. So vertical asymptote is x equals what makes the bottom 0. So we can plot those on our graph. Everything you find, I expect you to plot it on your graph. How do we do the horizontal asymptote? Limit as we approach positive and negative infinity. Okay, right now it's infinity over infinity, so you have to divide everything by the highest power of x. So if you take it times 1 over x squared, so then you get 0 over 1, which is 0. So the horizontal asymptote is y equals 0. Right. Are we still doing okay? Then I'm going to ask you to find your critical points and increasing, decreasing. So what do we need to do? So we have to do the quotient rule here. So that is low, which was x squared minus 4, d high, minus high, d low, over low squared. Multiply this out before you cancel anything. So we get a negative x squared minus 4 over x squared minus 4 squared. Does anything cancel? No. So critical points are anywhere this is 0 or undefined. If you set the top equal to 0, you get x squared equals negative 4. Can we do that? No, it's going to be imaginary, so we don't have to worry about that. So we really just need to know what makes the bottom 0, and that is plus and minus 2. So those are my critical points. So then what do we do to find increasing, decreasing? Make our sign line. So we do our test points. So if we plug -3 in here, the top would be negative, the bottom's positive, so that's negative. Put in a 0, negative over positive is still negative. If you put in a 3, you get a negative over a positive, so it's still negative. Can I say this is always decreasing then? Can I just say negative infinity to positive infinity?
No, because there's asymptotes.
No, there's asymptotes. So decreasing from negative infinity to -2, union -2 to 2, union 2 to infinity. Alright, so this graph is always decreasing. Do we have any maxes or mins?
No.
No, if you're always decreasing, there's no max or min. If we did, I would expect full ordered pairs, so how would you get the y values? Plug it into the original, okay. So then we need the inflection points, so we have to do the second derivative. So quotient rule, low, d high, derivative of the top is -2x, minus high, d low, so the 2 comes down, inside stays the same, subtract 1 from the power times derivative of the inside, over low, squared. What can we do here? So we need 2x cubed plus 8x. All right. 2 times 2x is 4x. Can I distribute the negative 4x then through here? So that becomes plus 4x cubed plus 16x. So we get 2x cubed plus 24x, or x squared minus 4 cubed. So my inflection points, we have to find out anywhere this is 0 or undefined. So if we set this equal to 0, what could we pull out here? 2x. If you set 2x equal to 0, you get 0. If you set x squared plus 12 equal to 0, what do we end up with? It would be imaginary, wouldn't it? It would be x squared equals -12. What else do we need for our inflection points? Yep, what makes the bottom 0, which we already know is 2 and -2. Alright, so we have to do our sign line. So if we plug in -3 in here, bless you. Then, let's see, we would get a negative. So -3 gives us a negative. -1, just positive. 1 gives us negative, and 3 is positive. So this thing is concave up from -2 to 0 and 2 to infinity. It's concave down from -infinity to -2 and 0 to 2. The only actual inflection point we can graph is when x is 0. And what do we get out when we put a 0 into the original? 0. That's the only true point because 2 and -2 are asymptotes. So when you plot inflection points on your graphs, remember you put the little x there. If we'd had ordered pairs for our maximum and minimum, we would have plotted those as well. So we've said our graph is always decreasing. When you have this asymptote, we could either draw it up here or down here. If it's decreasing, which one would it have to be? The down. And we know that the graph is concave down there, so that makes sense. We're decreasing but curved downward. we have to continue decreasing, but it needs to be curved upward next. So decreasing, so it's falling, but it's curved upward. And then I had an inflection point, and then it switches to curved downward. And then we're back to curved upward, but we're still decreasing, so still falling. So our graph should look like this. All right, so is there a polynomial function where f of 0 equals -1? So 0, -1. F of 2 equals 4. And the derivative is always less than or equal to 2. Okay. If it's a polynomial, that means we can do the mean value theorem. Okay. Mean value theorem says that somewhere the derivative has to equal the slope between the endpoints. So if I find the slope between these endpoints, so slope is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So we get 5 over 2. So that means the derivative has to equal 5 over 2 somewhere between x equals 0 and x equals 2. So is it possible that the derivative is always smaller than 2? No. It has to equal 2.5 somewhere, so it can't always be smaller than 2. So this was really just kind of getting you to think back to your mean value theorem. I think this was maybe a bonus question on one of the quizzes that we did. What else? Anything specific off here, or anything else you want me to make up an extra one like? I know we struggled with 15 and 16. Do we need a question like those again? Make up one like that? Okay, so getting you to think about these graphs. Let's say my graph did okay, here's my graph. Let's say that this is the derivative. So if that is my derivative, I want you to tell me where the original function had a max and where the original function had a min. So if this is the derivative, where do you have maxes or mins? What are my options? 0, -2, and 3. Your maxes and mins happen where your first derivative is equal to 0, right? Okay. This, since I don't have anything to the left, can this one count? No, it's just an endpoint. So let's go here. My first derivative was positive. That meant my graph was increasing, and then it switched to negative, so it was decreasing. So what happened at 0? A max. All right, at 3, it was decreasing and then switched to increasing. So that would be a min. And my reason is just because your derivative changed between positive and negative. Okay, that's when you have maximums and minimums, when it switches between increasing and decreasing. What if I asked you, where are the inflection points? So if this is the derivative, inflection points happen when what is true? Inflection points are where the second derivative is 0. So if this is the first, I need to know when the derivative of this would be 0. So what am I looking for on this graph? Horizontal tangent lines. So where would we have horizontal tangent lines? Okay, -1. Where else? 2. Where else? 4. Where else? 5. Because of those horizontal tangents. Is this making more sense? If this were the original function, so pretend this isn't the derivative. If it's the original, could you tell me where your inflection points would be? Where the concavity changed. So that would be at 0, maybe 3, and 4.5. So you just have to think about which one you're looking at and what it tells you. If this was the second derivative, if I was looking at the second derivative, where are my inflection points? Inflection points are where the second derivative is 0. Yeah. So we're just looking at for your x-intercepts there. Okay, so just think about what I'm asking for and how that relates to the graph given. Tells us my function is 1 minus x to the 2/3. All right, when you put in -1, you get 1 minus, this is what, saying the cube root of x squared. So if you did the cube root of -1 squared, you get 1 minus 1, which is 0. When you put in +1, you get 1 minus the cube root of 1, which is 0. So this is the third condition for Rolle's theorem. But I'm telling you, Rolle's theorem doesn't work here. Remember the first two conditions. That's condition 3. Condition 1 is it has to be continuous. Is this thing ever undefined? No, so it's continuous. We're good there. Condition 2 is that the derivative has to be defined. So if we do the derivative, we get a -2/3 x to the -1/3. So this is undefined where? Is 0 between -1 and 1? So the conditions aren't met, and we can't use Rolle's theorem.